email about it. You'll notice that one of the questions on there, I googled just for grins. I googled what is a p-value, and the very first link that I came up with on a Google hit had a wrong answer, which I thought was fantastic. I thought it was fantastic because that again goes to show you how little people understand what a p-value is, and that's what I started thinking about this week and what we should do this week. And I was thinking. Okay, we've done multiple proportions. Now we're in the middle of doing goodness of fit testing, which is testing proportions. We're in the middle of doing the M&M experiment, which we'll finish today. And then there's a secondary multiple parameters test called an ANOVA, which is actually pretty popular in research. And I thought to myself, man, maybe we should just focus on getting GOF done, goodness of fit, and then do an ANOVA, and then call it a class. And I said, you know, after having the very first hit on a Google search have the wrong interpretation of a p-value, I inserted a question on your take-home that asks you to fix the answer that was wrong. And I want to, instead of just cramming more tests into you guys, I just want to make sure that after today and Wednesday, or Thursday I guess, we have enough of a recollection of what those p-values mean. If I can get you out of here, have you leave this class with a rock solid understanding of what a p-value is. It doesn't matter what tests you run. On your out-of-class exam, the first thing you're going to do is you're going to analyze the multiple choice test I took when I got AHA certified for CPR and first aid. Because there's no test that you learn in any intro statistics course that allows you to test the results of that exam that I took. So I made one up. And maybe what I'm seeing is kind of strange until you realize what I did. And you'll be like, oh, that's totally bomber, what he did. But the whole crux of it is the p-value, understanding what the p-value is. So I figured rather than just cram another test at you guys, which I think is probably kind of ridiculous, let's finish up GOF, finish up the goodness of fit. I'll make a nod to the ANOVA so at least you know what it is and when it comes down at you, as it might later on in your lives. You may have already experienced it already depending on what classes you have, or you probably definitely will depending on your field. It seems like psychology studies love ANOVAs. When you're testing a whole bunch of averages. We'll talk more about it, but not get into it. I can't do it justice in a day and a half anyway. There's way too much involved in an ANOVA to just cover it. I can teach you how to plug numbers into a machine, but that's dumb. I'd rather have you have an understanding. So let's finish up GOF. Let's finish up GOF, and then we'll do a big kind of overview of where we're ending up with in the course. Kick you out of here. Come back on Thursday. Talk about next week. Call it a day. Maybe we have a project on a project for Thursday. Linear. A couple of them have come in already. Some of you guys have emailed them in already. It's an email submission project this time. No print. I don't want you guys to print them because if you print them wrong, you end up having 25 pages of Excel spreadsheet. It's hard to look at. I know. Kind of annoying. So just an email submit. You email submit it. It's all in the text of the document. So I think I posted a quiz too for Wednesdays. Well, on goodness of fit, which we're in the middle of doing right now. And I want to tie back to what Laura asked me on Tuesday. It's been a week and I remember this. Because you said, can you only test randomness with goodness of fit? Because the very first thing we did was test that iPod randomizer to see if it was being random enough. And our vote was that it was the iPod being random enough? Do you remember? It's been a week. It's okay if you don't. Weren't here, that's okay. Didn't watch the video? Damn. That's harsh. Was it being random enough? I hear a very small no. I hear a slightly louder yes. A bunch of pages rustling, that's okay too. So basically, we shook the randomizer 50 times, kept track of the songs on it, and we got a p-value based off the goodness of fit test, which I painstakingly made you guys create up here on the board, which I'll never make you do again. That was a one-time only thing. It's different enough from the rest to see what's going on, but once it's done, it's done. It's technology. We get a big or small p-value that time. We got, good, Drew, be ready. It was huge. It was humongous. It was a humongous p-value. And the idea was, you go into the test assuming the iPod is random. Because our claim is that Apple was messing with the randomness. That was our claim, that Apple was messing with the randomness. That would be your alternative hypothesis. Apple is messing with the randomness, therefore we're seeing certain songs more than we should be seeing them if it were being truly random. A small p-value would have us believe that. And we did some random. I'll do it again, in case you don't remember. I had a simulator set up to do just that. Random songs. Here we go. So here, you can't see that. We ran this a few times on Tuesday. Here are 20 randomly selected songs using the random command in Excel. using the random command in Excel. So this would have simulated exactly what me and Chris did up here at the computer where he's shaking the iPod 50 times to keep it track. So every time you see a 1, that's a pet, then a tar, 10 I think was a Run DMC, Iron Maiden might have been 7, I forget which song was, but it doesn't matter anyway because it's just randomly assigned. So right now, here are the results of that particular 50 trials. iPod being random enough? iPod being random enough? Based on that? Absolutely. Look at that p-value. It's humongous. It's humongous. 88%. The larger that is, and it's the same, the p-value for this is the same as the p-value for anything else. If it's below 5%, something's changed. That's huge. Humongous. 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 Let's do it again. 50 more songs. What do you think? iPod being random enough? Wait a minute. There's only one occurrence of song number 9. That was Anthrax and Public Enemy. That's crap. But is it being random enough? Yes. You can have those little dips. That's the beauty of a goodness of fit test. It allows for what seems to be inequity in the random process. It does, doesn't it? It looks like something's wrong because there's far too few of those and far too many of this. But it measures all of it as part of a whole and says, you know what? You're going to have that. Over time, you're going to have those clumps. How about now? Okay? 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 Let's see if we can find what's not okay. One happened on Tuesday, you might remember. One showed up where a song didn't show up at all. A song did not get heard. I'm probably going to find it again because it was dumb luck.
Ooh, that was it.
Oh, was that it? I was looking at the wrong damn thing, sorry. Close.
0.04.
0.04. Scheiße.
Oh, wait.
That was 2.8, right?
I think you just had a beginning.
Sorry. 0.8.
Oh, no.
I should be expecting something about when.
Now.
Close. About when?
Oh.
Give me a number.
There we go.
1 in
4.
20.
Oh, 20.
Remember, 1 in 20, I should be getting a false positive. Yes? False positive means it's being random, but I flag it as not random because of something like this. Now, if you look at that carefully, it doesn't look that much different. It doesn't look that much different than the other graphs, but you have to also make sure you look at the scaling. There are 13 occurrences of Iron Maiden now, which would make Chris very happy were he here. But there are far too few of these guys here. There should be 5 of each on average. That shows too much deviation from average. So there you go, that's a false positive, because it was working randomly, because I'm using Excel's randomizer now, not the iPods. But it's still flagged as a false positive. The same kind of errors can still exist. So we would have made a type 1 error here. In class, we could have made a type 2 error. Because in class, remember, we had a big p-value, which means we said, yep, randomizer's working, negative test result. Could be wrong. I'll never ask you to calculate the chance of that happening on the goodness of fit. It's because it's a pain in the butt to calculate it manually. Cool? Ish? But more, this is just testing the randomness. You can also test non-randomness, but a certain distribution. These tests, let me shut this down real quick. These tests are called goodness of fit tests. Because you're not necessarily testing a random fit, you're just testing to see how well data fits to an assumed proportion. So these are called goodness of fit tests. And that's why the program I gave you is called GOF, goodness of fit. So the idea is you have a multinomial experiment. Multinomial experiment. Now think about what that might mean. Multinomial. Sounds kind of similar to the word you already know. Another nomial word.
Binomial.
Which is binomial. What was the deal about a binomial? What makes a binomial binomial? A couple things. Give me one.
2 mutually exclusive outcomes.
2 mutually exclusive outcomes. Perfect. 2 mutually exclusive outcomes. One of the trickier ones you might not remember is a fixed number of trials. You have to do an experiment a certain number of times and then stop. Not until you get a desired result, but until you're done. So binomial, 2 mutually exclusive outcomes, fixed number of trials. This is the same, except instead of having just 2, you can have 3 or more. Yay! That's fantastic. That's fantastic. That's fantastic. Do you remember why I had Chris shake the iPod 50 times? Do you remember that? Why I had him go? I had to stop at 50. We could have gone more, but we shouldn't have gone any less. Do you remember why? It's okay if you don't. It's been a week, and Thanksgiving, a lot of turkey in between. I'll give you a hint. Does this ring a bell? N times P. That might not ring a bell from the binomial days. It's okay. It's been a while. I haven't been picking on this very much. You have to make sure that theoretically, in order to see enough data, any probability you're using in the sample, in this case it was all 10%. It was all, because if we had 10 songs, we're assuming each one shows up 10% of the time. You have to make sure your sample size is large enough so that that times 10% is at least 5. I should say they're equal to. And 50 makes it at least 5, because 50 times 0.1 is 5. If you did more shakes, you get more data, and therefore maybe a more complete picture of what's going on, but 50 was the minimum. And I've noticed that around 40, you guys start getting bored. You're tired of just sitting there watching somebody shake an iPod and me click buttons in a spreadsheet. So that's kind of, this is the same n times p bigger than or equal to 5 that we had back with the binomial, exactly the same. Back then it was slightly different. Back then the assumption was that the normal distribution will kick in. That was why we did that, to make sure that the bell curves would appear. This doesn't care about bell curves. This is one of my favorite tests, and here's why. It's non-parametric. Non-parametric. Remember what that means from your last project? What non-parametric means from your last project? And if you don't, that's okay. You're going to experience one on the first problem of your out-of-class exam, your last out-of-class exam. What does it mean? Do you remember? The last project was about the oil spill in the Gulf of Mexico. What did we have to do with that? Besides open Excel and make you do geometry, which I know is a bastard. I should do some geometry now. Did you run a t-interval? Did you run a t-test or a t-interval to approximate how much oil there was? Did you go to your TIs, use a t-test or a t-interval? Hell no, you didn't. No, why didn't we? Why didn't we just do a t-interval? You need a low and you need a high, make a t-test or a t-interval. What was the problem with the data? Tightness. I see it's erased everything. There wasn't enough of it. Now what is that? Danielle, is that right?
There wasn't strong.
Say it again. Well, we could approximate it from that video. We had 6 flow rate approximations from that video. That was all the data we had though. But 6 isn't a problem except for what was the data shaped like? Do you remember? Was it shaped like this? No, oh god no. It was shaped like this. It was shaped completely wrongly, incorrectly to use a t-test. So the problem with a t-interval or a t-test is they're parametric tests. What that means is, and this is one of the problems with 244 as I see it, we focus on these almost exclusively. Every time you start a test, I verbally say this, I don't make you actually crunch through, because nobody actually does. I say you have to make sure that n times p is bigger than 5, you have to make sure the data is bell-shaped, you have to make sure there are no outliers pulling the average. All these concerns about things so that the data fits a certain shape. And that's important if you're going to use those tests. The problem is there's a whole class of tests called nonparametric. You've done 2 already in this class, maybe even 3. You did project number 3, which was the nonparametric approach to the t-interval. You did the Likert scale analysis in your last homework set, which was how to deal with data when it's ordered but not spaced, like numbers should be. Strongly disagree, disagree, no neutral. You're going to do the one on your last exam, which is how to deal with a 4 selection multiple choice test, which doesn't have any test that fits. But all of these, goodness of fit is a 4th one here. All of these don't care. You don't have to go into those and say, okay, is the data bell-shaped? Because it doesn't care if it's bell-shaped. It doesn't. Ours happened to be for M&Ms. It didn't happen to be for the randomizer, because the randomizer should have been uniform. And the beauty of these tests are, they don't care about what kind of data you have. They can deal with it on the data's own terms. And that's what I love about it. Oh, your last out-of-class exam had one too. Ah, remember that one? It was the seizure rate one. And you did it in Excel. You might not have realized what you were doing. But when you held down F9 and let that curve show itself, and the little yellow section popped up on the curve, that was a non-parametric test. You assumed 25% infection rate, or seizure rate, not infection rate, seizure rate. And you said, what would the curve look like if it was actually 25%? It ended up being a bell curve. But nowhere did you have to assume it was, it just showed itself to you. It showed itself to you. That's good. That's good. It's kind of what I like about the discovery of statistics, using this. I don't have to sit here and tell you, fill your head. That's why the central limit theorem was so nice in 243. Here's a bunch of dice. Go roll them and count what you get. Oh, look at that, a bell curve. I didn't come at you and say, hey, there's going to be a bell curve. You rolled the dice, sat to happen again yesterday in 243. Students sat back and were like, what the hell's a bell curve doing up there? Exact words. What the hell is a bell curve doing up there? Because they had just gotten done looking at the non-bell curved parameter distributions. And then they got these bell curves. What the hell is a bell curve doing up there? I don't know. Let's explore further. And that's the beauty of it. These show you the curves on their own terms. Yay. So that's why I like goodness of fit testing too. ANOVA is another parametric test. You got to make sure the data's bell-shaped with the same variances and all kinds of conditions. So, well, more about that later. More about that later. So, Laura, not just random. We can also test, well, not just uniform. I want to say not just uniform data. Because all the data is somewhat random. I mean, I gave you all a bag of bananas, had you crack them open and count the colors. There's some randomness in there, yes? Definitely. So, here's what we got. Here's what we got in class for our M&M results. What I want to do is I want to test them to see if that is within the realm of acceptable. So here's our data right here. Oh, goodness. Here's what we got right here. It's kind of hard to see. I'll put it on the board momentarily. These are two theoretical distributions of colors M&Ms have given me over the years. We're going to test this one. This is the most recent one they've given me. This one was up till about 2008, and then they stopped that one and started this next one, which is a shame because this one's actually more annoying mathematically. This is what we got percentage-wise our term right now. Those are the percentages we got. This is the percentage we should have gotten. Notice the difference. Yeah, there's somewhat of a difference. We should have had 13% red, we had 6. We should have had 13% brown, we have 18. 20%, 20%, that looks good. 24%, 16, 16, 25, and 14, 15. Some of them look fine because they're almost exactly the same or maybe 1 percentage point off. Some of them are far apart, but it's hard to measure far until we know what the margin of error is on the estimate that we're getting. And that's what GOF does for us all at once. It measures them all at once. Just FYI, this is what we've gotten over time from 2006 to the present day. That's the percentages I've gotten. Which, if you look, have less variability from this than this does. Right? But still variability. Oh, thanks, Will. Thank you very much. Less variability than our current term does, but still variability. And you would expect less variability because this one has a humongous sample size. I don't know where it's listed up here. So here's the mass totals right here that I've gotten over 8 years. So that's our job today, is to test to see if we're close enough to what M&M says we should be. Now some of you are thinking like, why is this dumb? This is dumb. It's M&M's. How does this tie into life? Well, it totally does. Because if you have proportions of population for a given area, that would be like the proportions of certain colors in a bag of M&Ms. And you can see if those are changing over time. Is there a larger proportion of disadvantaged students coming into COCC? If so, can we break them down by some qualitative category? Red, orange, blue, green becomes southwest, southeast, northwest, northeast, north central, south central, for example. So this is the exact same mathematics that can be done, but it allows us to get away from the uniform distribution, Laura, and get into a non-uniform distribution, but still somewhat random. Cool? All right, so let's state our hypotheses. If we think something's up, which it looks like it might be, it looks like something might be up, what are we going to go into our test assuming? Like we always do? That everything is? Oh goodness, Thanksgiving has erased everything. It is not. I'll dig deeper. When you go into a hypothesis test with a claim, our claim is that something's off, yes? I don't know where. It looks like give me one color that looks like it's off, significant.
Red.
Green, red, yeah, green and red, they definitely look, how about blue? 2416, or is that close enough to you guys?
Those are.
That's far? Okay, so blue may be off, green might be off, yellow is okay, I think. Red, yes, how about brown? 1318?
Yeah.
It's questionable, yeah? It's hard to tell on that one. 2020 looks okay. So it looks like there's some colors off, but I'm not going to go in there and actually state these 3 colors are off. I'm going to say I think some colors are off. That's basically what I'm going to say in my claim. That's my alternative hypothesis. Let's shut this down and swing it over here. Thanks for killing that light, Will. I appreciate it. Swing it over here. So my alternative hypothesis, I'm not going to say which, but I'm going to say at least one of the colors percentages is off. At least one is off. That's what I'm going to say. If that's the alternative, what's the null? Which you do need. You need the null to test this, the alternative claim.
That everything's the same.
That everything's the same as what?
As what they...
Yes, thank you, Rosie. That everything that they said we were going to get, we're actually going to get. In other words, that the percentage of red is actually going to be 13, which is the same as the percentage of brown. We should actually see 13% red and brown. We should see 14% yellow. This is where it gets ridiculous in my opinion. This is why I like their old percentages, 10, 20, and 30%. Made a lot more sense than getting down to 1 percentage point of difference, their claim. We should have 16% green. I'm just making a laundry list here, friends. 20% orange and 24% blue. Hopefully that adds up to 100. 44, 60, 86, it does, 100%. So 100% of the time you get one of those 6 colors. Our job to see if they are, arguably. Well, what's on your mind, my friend? Or you're just crunching numbers? Okay, I see your brow furrowing, sorry. It's my amphibian, I'm doing it again, Laura, I apologize. So, our job is to see if we are close to that. And when I say close, it doesn't have to be exact. I'll read something to you after the break here in a minute. But close enough to that, those numbers to be arguably the same, even with a margin of error. Okay, doke? Alright, so the only thing you have to do, I made you do it out with the iPod math before, I will never make you do that again. Only because it becomes tedious. You saw why we had to do it once. Let the technology take it from the rest of the time. First of all, we have to create an observed column, and we have to create an expected column. You need both of those columns. That's what you're going to be feeding into your TI, or any other goodness and fit test for that matter that you use, whether you use an online applet or Excel or something else, although Excel doesn't have one. So let's keep track of this. Let's just put the colors down the side here. We'll do, we'll just go in order, I guess. Red, brown, yellow, green, orange, and blue.
Is observed theirs?
No, observe is what we saw. Thank you, Rosie. Good question. Observe is what we see.
Oh, and so the other one's expected.
Yes.
Experiment.
Expected would be what we should have seen. Very good question. Thank you for that. Observe is what we see. So when we did the randomizer on the iPod, that's the number of times we saw Pat Benatar, we saw Iron Maiden, we saw Run DMC, we saw Queen. This is what we should have seen. And when I say what we should see, it's under the null hypothesis. So assuming the null hypothesis is actually true, that's what we should see under that assumption of the null hypothesis being true. Thank you. Great question. Great question. Great question. So all we got to do is just write down our observables right now. So let's see. Red and brown, we saw 54 red, 162 brown. We saw 129 yellow.
We don't have like real numbers for the expected.
We'll get to that. Danny's got a great question. We don't have real numbers for the expected, but we have everything we need to get those numbers. Hold that thought. Thank you. Thank you. We're going to go back to the randomizer from the iPod again and then come back to this. Green, we have 217, yes? Fantastic question, Danielle. Thank you. 173 orange. And blue was 142. Good. That's what we saw. That's what we saw. And now, what Danielle said is great. She says we don't have real numbers. So, in other words, all we have is what for the expected? Percentages. Good. Now, what you don't want to do is put percentages in here by themselves, because then you're comparing apples to oranges. You have M&Ms here and percentages of M&Ms here, and that's not what you want to do. You don't want to crunch it that way. This is what we actually saw data-wise on Thursday. So how can we fix Danielle's awesome point in that we don't have any numbers to put here? Can we put numbers there? Think. Go, Kelly.
If we do, what's the total number of M&Ms?
I'm gonna cheat. 877. Excel tells me.
So can we like take the percentage of each? Like, does that make sense? So if we're supposed to have 15% yellow, we take 15% of 877.
That's exactly what you're gonna do, my friend. That's exactly what you're gonna do. It's the same thing we did for the iPod shuffler. Now, the iPod shuffler was easy because we were expected to see 5 songs every time, but that's because 50 times 10% is 5 every single time. Right. All we gotta do is adjust it for our new data, which is a different percentage thing. It's perfect. So for the red, we saw 54. That's what we saw. Assuming the null is true, we should have seen 13% of the 877 that we saw total. So 13% of 877. I'm going to let you guys crunch the numbers while I crunch through here. Brown should have been the same, yes? Also 13% according to according to what Mars told me, yellow should have been 14% of that 877. Green should have been 16%. Orange, 20%. And blue, 24%. Oh, sorry, 77. What will that sum up to? What will this whole column sum up to?
Should be 877.
It'll be 877, it has to be. And that's why I double check these percentages summing up to 100.
Should we just put whole numbers under expected? Or-
Leave the decimals, Laura.
Okay.
Just like in 243, sometimes you have 2.5 children per family. But that's an average, right? That's completely legitimate. And you can enter, if you don't want to do a secondary step, you can actually enter these computations directly into your lists. You don't have to do it once, get the answer, and then enter it into your TI. I'll do it in the TI for you. I'll show you what I'm talking about. So this is what I would put. I would definitely put one of these in L1 and one of these in L2, and then just keep track of it. I tend to put the observeds in L1 and the expecteds in L2, and then run from there. Let's crunch it. Shut this down. Spin the camera around. All right. You guys are going to be ahead of me, that's okay. Get myself caught up. Great. All right, so L1's got I'm going to do a quick double check, make sure I did that math right. I'm going to sum up list 1. Okay, I'm going to sum up list 2. Okay, we'll go with it. I mean, I think I'm good. I got the same sum on both of them, which either means I screwed everything up perfectly or I didn't screw up at all. I'm going to go with didn't screw up at all. I think screwing everything up perfectly would be even less likely.
How did you get the sum command?
Oh, second stat. And then over to math, and he's 5 down from there, Laura.
Okay, I see.
That's one of those ones I sneak in every once in a while. I forget to tell you guys about. It's just a double check for me, because if I'm working too rapidly, sometimes there's all kinds of neat stuff in here. This is all, what you can do is you can grab any of those commands, and then you stick a list name in there, and it does that. Like this product will take the product of an entire list. I've used that in the past. When I use, not for you guys, but for 105, if you're counting random, how many times you have to replicate an experiment until you see at least one of each occurrence, you can use that command. Pretty handy.
Can you tell me what you do after you put it in there?
Oh, we haven't gone any further yet. Yeah, we got the data in. And you have to get L1 and L2 observed and expected in first. Once you got that, then you're ready for the TI to take it the rest of the way. So we need a test statistic and a p-value. Yes, here we go. So it's under program. Go find Goff. Find Goff. And then just run it. It's going to ask you where your observed and expecteds are, L1 and L2. So second 1, second 2, and that's all it needs. From that, it can do everything else. And it's going to tell you the test statistic is 116, chi-squared, which honestly doesn't tell you a great deal without the p-value. So now you got a test statistic, which is chi-squared. We'll come back to that in a second. About 116. What's the p-value come out as? What's the p-value come out
I
as?
did the 0.13 times B.
What's it tell you? What does this tell you? What's that tell you? What's it always tell you when it's this small?
Reject the null.
Reject the null. Null is garbage. The null is garbage. What is the null again? In this particular case,
It's the same.
it's that whatever Mars told us is right is most likely not right. So, in other words, we can't believe this. There's no way we can, remember our original assumptions was that something was off in some of the colors, the greens and the blues and the reds were too far off. This tells us our assumptions probably are correct. There are some things off. So the conclusion now is that, yeah, at least one of the colors is off. Rosie?
Wouldn't their statistic come from a much huger sample? So
Very true. But this controls for our small sample. That's the whole point. Thank you, Rosie. Rosie's point is their data should come from a much, much larger sample, therefore should have a much, much smaller margin of error. Yes, but this goodness of fit allows us to incorporate our smaller sample and deal with it that way. Thank you. That's 100% correct. Now, it should be fair to note that this happens every single time I run the experiment, just so you guys know. So if you can see collectively, I've collected data over time. But I want to come back to that momentarily. Which colors are off? With statistical certainty, please. That gets hard, doesn't it? That gets hard, doesn't it? What colors, at least which color is off? You can give me at least one that has to be off. And you might not know this exists yet. Go back to your TIs and look at the stat edit screen. I'll swing this back around here. And you might not remember this from last Tuesday, and it's totally fine if you don't, because it's been a long time since last Tuesday.
Definitely red.
But good. But I had you guys calculate this by hand with the iPod. And we had 6 columns or something on the front board. The last column of which, if you might remember, and it's okay if you don't, was the O minus E squared over E column. You might remember that vaguely from class on Tuesday. That's what we worked up to, was that right there. That column I left in the code of your program. Check it out. When you go to stat edit, L3 is that O minus E squared over E. That's the value of that for red. That's the value of that for brown. That's the value of that for yellow. That's the value of that for green, orange, and blue. So, the larger these numbers are here, what? The more off they are, exactly, Rosie. The larger those numbers are, the more off they are. Which means we got some that are pretty close. We got some that are pretty, looks like yellow's pretty close. Looks like, what's that? Orange, damn close, yeah? But then it looks like a bunch are pretty far off. Now, this is why I have to mark this carefully, verbally carefully. Number one, that one is clearly, no, excuse me, right here, it's clearly the most off. 41 is the most off. 41 would be green. Green is too far different. Green was the 20, I think it was 24 and we ended up with 16. We saw 24, it should have been 16. That was too far off. The question is 31 and 20 and 22, are those too far off? That's something you don't get into with a Hoc test. You get into what's called post-Hoc testing, which I'm not going to get into right now. We'll get into that in your homework set for Thursday. That's when you actually go back in and you hyper-analyze each piece and you go, okay, is this too far off? Is that too far off? Is this too far off? But you have to do some corrections so you don't lose confidence by doing that. So we'll get into that for Thursday. We'll do that for Thursday. But what I want to do right now is, I want to share something with you. I told you this happens every single term. So I carefully wrote a letter for us, addressed to my M&Ms. To whom it may concern, hello and greetings from beautiful Bend, Oregon. This is your tri-yearly letter to assist you in the quality control of your colors. I applied some graphs. That's the graph they gave us, we should have. That's the graph we got. These might look familiar. And then I basically just walked through the strategy that we did. Just what we just did. I did the exact same thing we just did. There's our 114.01, and so forth and so on. There's all our numbers. So then I explained to them what a chi-square test statistic is on the back. Told him it's equal to 116.3. And then he says, what does it mean, you might ask? The value is a standardized measure of how well correlated our observations are to Mars. And then I got pretty wordy. Now, the thing is, remember the p-value said it was 0? It's actually 1.9 times 10 to the negative 23rd. Which is basically 0, right? You guys are like, that's pretty much 0. Now, the thing was, I realized as I'm writing this, every term I write this, and I'm like, they don't give a crap. So I decided to put it in terms they can understand. Check this out. And I use this in court. Whenever I'm asked to go to court or submit a document for court, this is what gets judges' attentions, lawyers' attentions. This result would be like taking a fair coin, flipping it 79 times and having come up heads every single time. Now, if that happened, would you think something was up? Yeah. You would think, yes? I mean, it's possible to have a coin come up 79 times in a row heads. But is it probable? No, it's not probable. You think something was wrong with the coin. It's like taking a normal 6-sided die, rolling it 29 times, and having you come up with the same number every single time. Is that possible? Highly improbable though, yes? Totally possible, this is my favorite. This is like if I had a deck of cards, fair deck, and I dealt Cassie 5 of them, and she got a royal flush, would you say, wow, that's unusual? Imagine if I did it 4 times in a row. Deal, 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 royal flush, take them up, shuffle them. Deal, 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 royal flush, take them up, shuffle them. 4 times in a row. Ridiculous, yes? Completely ridiculous, but that's what that probability is equal to. This is what gets people's attention when they see that. They're like, okay, something's up. Now the assumption of all those things is that the coin is fair, the die is fair, and the deck of cards is fair. But it's extraordinarily hard to believe that they're fair when you get these results, yes? So what do you believe about the deck, or the die, or the coin? That they're fixed in some way, just like I think their percentages are fixed. So, it should be noted these results are consistent year after year. 8 years of data right there. It is most likely the case your machinery is not calibrated to the proportions you are claiming. So, and I put a little footnote here. In previous emails I received from customer care, it was stated that each large production batch is blended to those ratios and mixed thoroughly. And I refute the entire claim because it's bogus. What they're saying is, we're being random. But what I'm saying is you're not being random. Or at least you're not being random to the percentages you're claiming. To assist you in quality control, we, the undersigned, need you guys to sign this. Have a simple solution. Please send us at your leisure a large randomly selected batch of milk chocolate M&M's candies. We will be happy to test this batch for uniformity across your percentages again. Heck, we'll even take whatever distribution you actually are achieving and statistically support it so you can stop getting mail like this from us every 3 months. Thank you for your time. We look forward to hearing from you. FYI, I hear from them every 3 months. Same form letter, except Jeffrey Wynn. There's always a different name on the bottom of the letter. Probably these poor people drink heavily, go to work, and have to deal with people like me all day long. Jeffrey Wynn, though. Jeff, if you're listening, he actually got into the form letter and put little thank you for your regular. Thank you for your inquiry. Jeffrey put, thank you for your regular inquiry. I'm like, ooh, that's a new word. I've got 8 years of these letters. If you've been in my office, you see them outside the door. They're hanging on notepads outside the door. There's my letters on the left, the rejection letters on the right. So Jeffrey actually got in there and made me like a slightly customized one, so I have hope. I feel a little like Andy Dufresne from Shawshank Redemption, constantly sending the letters. I'm going to keep doing it until I'm old, grizzled, and gray and retired. Maybe I'll get some candy then. So we're going to take our 5. If you guys would be so kind as to sign your names on the space down here, kind of squeeze them in. We'll get it in the mail. Check with me in a couple months.